So thanks, Young and Must folks, for having me present my recent and not so recent work. This presentation will be about the effects of disorder in Mott systems. This is work that I've been doing for a number of years, starting in the early 90s, and it keeps on going. So I will just like to give a big overview of some of the highlights of our results without going into too much detail. Before I go on, I would like to acknowledge here the National Science Foundation for keeping me on payroll, which is very much appreciated. There will be a lot of different papers that I'll be touching upon, but I didn't want to give a list of all these papers. I just gave some review articles here, some literature, and one can find many details in these review articles. But without making a long list of collaborators that contributed, let me just mention that a large part of the work has been done together with my longtime collaborator, Eduardo Miranda, and in fact, many of the specific results were produced by a number of graduate students who we co-advised over the many years we have been collaborating. The first review article has been written some years ago, but some more recent references can be found in the remaining references here. So I already mentioned in the previous presentation, I gave a broad introduction to what is the metal insular transition as a sharp transition existing only at zero temperature. But then as the temperature is increased, then we can see really the difference between the metal and insulator in its temperature dependence. When you look at that, you find that there's an intermediate region which is not similar to either a metal and an insulator, and that's pretty much the focus of the field of metal insular transitions, to understand the so-called quantum critical region around this kind of phase transition, and in particular in systems without having any magnetic or charge order or base symmetry breaking, where the main physics is just driven by two major effects that can stop the electrons from moving. So traditionally, people discuss two mechanisms to stop electrons from traveling in a solid. One is due to Phil-Anderson. Impurities can form bound states and the electrons can stop moving. Or if you have narrow bands and strong repulsion, Mott pointed out that strong repulsion can also lead to an insulating state without change of symmetry. Both of these limits are understood to some extent. But when you have them together, this is actually not very well understood, although in most materials you have both of these effects together. So one of the big questions is, do interactions help Anderson localization? Does Anderson localization help not Mott localization, or they oppose each other? This is one of the big open questions in the field. And before I start presenting my own results that we obtained over the years, let me just go back in history and remind you of what Phil-Anderson said in his famous Nobel Prize-winning lecture in 1977, which can easily be found online. It's entitled "From Local Moments to Localized States." And in this lecture, he said the following: "The second reason why I felt discouraged in the early days was that I couldn't fathom how to reinsert interactions." He's talking about Anderson localization, and was afraid they too would delocalized. This realization, of course, that Mott insulator localizes without randomness because of interactions was my liberation on this. One can easily see that Mott and Anderson effects supplement, not destroy each other. So he felt that because both mechanisms can help stop the electron moving, then when they have them together, the effect will be even stronger. What I would like to try to do today is to tell you that this is completely wrong. In fact, not maybe always wrong, but there is a broad class of systems associated with the vicinity to a Mott insulator where something totally different happens, and we have today good theoretical but also experimental evidence of the fact that interactions and disorder don't always like each other. In fact, they oppose each other in some very specific ways. So this is, if anything, this is my take-home message for today. And now I would like to show you some examples of that. The reason why we have been able to make so much progress is because not only we have some development in the theory side, but we also have a number of new systems that have been developed and refined experimentally, and that allow us to study the Mott transition, specifically the Mott transition in half-filled bands, where you vary the Fermi energy either by changing the carrier concentration or by simply applying pressure or some other parameter. And that way you can go through a transition from an insulator to a metal and study its detailed properties. That includes various two-dimensional electron gases and semiconductors, but also more recently discovered quasi two-dimensional charge transfer salts, more so-called Mott organics, and even more recently, a year ago, there's a new class of transition metal dichalcogenide moire materials that are in fact fantastic realizations of a single band Haber model. So as you can see from these plots, and you've seen them before, the transport properties and all other properties, in fact, of all these examples are extremely similar, and they give us a very good way to test theoretical ideas and to discover also by a variety of experimental probes what happens near a Mott insulator. So here is the chart of my talk, a big map of what I'm going to be discussing today. This is the phase diagram of half-filled Mott transition. And there, as it turns out, there are various regimes in this phase diagram which differ a great deal in terms of how the electron moves, what is the mechanism of transport, and the entire electron dynamics is quite different. And in fact, what I hope to convince you is that the effects of disorder are also very different in these different regimes. So there is not a single answer, what does the disorder do? You have to specify which regime you're talking about, and then you'll get very different answers. And I will go around this phase diagram from the insulating phase all around high temperature and then coming back to the metallic side. And I'll like to show you how some of these regimes are not very sensitive to disorder and others are quite sensitive to disorder. So the theoretical approach that we'll be using here and also testing in comparison to experiments in dynamical mean field theory. We heard a lot in this group about dynamical mean field theory, so I will not elaborate much. Here's the single band Haber model, and most of the results are obtained in the simplest so-called CPA approximation. That's one of the things we'll be working on in this group, where you compute some physical properties on a given site, which depend on the site energy in a random system, and then there you perform an averaging, which then gives you a description of the environment of a given site, which in this approximation is taken to be the same for every site. There are systematic improvements of this, but this is the simplest approximation, which actually becomes exact in the limit where the number of neighbors becomes very large. So this is a very reliable limit where we can really test some theoretical ideas. So let me start my discussion from the insulating side and start by asking a question. If we have a Mott insulator, like shown here, this is the density of states that has a Mott gap. Mott gaps can be substantially large in some cases. And then you add some disorder. The disorder is always present, and you want to know what happens if you add disorder. How is the Mott insulator influenced by that? And in particular, we'd like to know how the charge gap changes. And in infinite dimensions, in the CPA DMFT approximation, what you find is that the leading effect of disorder on the Mott insulator is simply to broaden the Haber bands. And the net result is the fact that the Mott gap is reduced. So that means that if you want to open the gap, you have to go to slightly larger interaction U, which is the splitting between these bands. And as a result of this, the critical U, when we vary disorder W, increases. So the Mott insulator shrinks when you increase the disorder, and the metal becomes larger. This may sound crazy. Adding disorder, you make something more metallic. And in fact, it's completely opposite to what Anderson just suggested in his wisdom. But this is what this is in fact an exact results in the limit of large coordination. And we can in fact look at some experiments. Here are the experiments on these quasi 2D systems by Kanoda, who took one of those Mott systems given by similar phase diagram. Here you see a Fermi liquid at high pressure. At low pressure, you have a Mott insulator. There's a first order transition line, which describes the coexistence region, and it's even superconductive low temperature. What he did is to take the system and to apply high energy X-rays to introduce systematic disorder damage to the samples. And the radiation time shown here, 0 hours, 50 hours, 70 hours, it means that the disorder is being increased. And what he found is that as he does so, the metallic phase grows and the insulating phase shrinks. And also the coexistence region, given by this first order line, also shrinks. So this is totally in agreement with the predictions of our theory. And in fact, these are the results obtained, even some of them early on in the early 2000s by Carol Ogiar, who was a former student of Eduardo and myself. And she produced this following phase diagram, which completely agrees with this experiment. So this is the first glimpse that that the disorder, in fact, can in some cases suppress under a Mott localization and not help it. Next, we would like to ask if we now start reducing the interaction strength or increasing the bandwidth and go to higher temperature, where the Mott gap starts to close gradually. We can ask what happens in this high temperature regime here, which we denoted as a quantum critical regime. This is pretty much the boundary between a region which has a Mott gap and a region which is some poor conductor, but without a gap in the density of states. And you may ask what happens here. Well, what happens here was first discovered in her famous work, which he did as a graduate student by Anya Terlecka, and now confirmed by many experiments. What she discovered is the precise trajectory, which can be understood as the trajectory where the Mott gap is suppressed. We can obtain such a result with DMFT. But she found more that there is a region around this line, which some people call the quantum Wisdom line, where which looks very much like what we expect for any critical point, in particular quantum critical point, where a number of physical quantities display beautiful scaling. So here is the family of resistivity curves that she obtained for different interactions as you change temperature, and by an appropriate scaling procedure, which is that of which is expected for quantum criticality, she found perfect, beautiful scaling, and in fact, some surprising mirror symmetry of the metallic and insulating branch. Anya met Kazushi Kanoda in a conference where I was not present around in the early, maybe around 2012, where I was still at Florida, and she convinced him to try to look for that in the experiments. He did it, and in 2015, in Nature Physics paper, he confirmed very beautiful scaling. Here is the result obtained in that first paper, completely in agreement with her theory, including the beautiful mirror symmetry of these resistivity curves. But he in fact did more, and he applied disorder to this system, and he found that indeed, just like our previous theory by Carl Ogiar predicted, the critical interaction U shifts up, so the metal is enhanced and the insulator shrinks, but also the coexistence region or the temperature of the critical endpoint TC is suppressed. Nevertheless, this high temperature region, which now becomes broader as we suppress the coexistence region, is apparently not changed at all. So this is what calculations by Carroll, which were extended in 2015 to look at the quantum critical region, as well as these experiments show that the scaling curves are almost identical. The exponent is within uncertainty the same. So that means that the disorder plays a very, very little role in this high temperature regime, except for shifting the transition to stronger disorder by broadening the Hubbard band. So this is a pretty dramatic discovery that, again, what Anderson said was completely wrong in this high temperature regime, which is really a very different beast, and I'll return to this then, how we normally think about a metal. Then we can go further, and we can reduce the interaction even further and start lowering the temperature, and then we are approaching now metallic regime. Now, something very dramatic happens in this regime, and what happens is that at low temperature, we have on the metallic side of the Mott transition, we have heavy quasi-particles. We have a strongly correlated Fermi liquid, which upon heating evaporates, and this destruction of these heavy quasi-particles happens around a temperature which some people call the Brinkmann-Rice temperature, because they are the first one to calculate in an approximate theory the energy scale of these quasi-particles, and that's related to the temperature scale that's needed to destroy them. As you can see, this temperature scale drops and approaches zero as we approach the transition here. To understand slightly better how this happens, Let me show you the density of states of a strongly correlated metal. You see the Hubbard bands are now almost touching, but there is a new feature. This is a quasi-particle band or quasi-particle peak here in the middle that describes these heavy quasi-particles. It has a very small spectral weight, Z, which is inversely proportional to the effective mass of these particles, which can be directly measured, and it has been measured in a number of experiments. As we approach the transition, Z shrinks to 0, as Brinkman-Weiss predicted, but M star diverges, and now the quasi-particle becomes very fragile. What happens to this quasi-particle as we raise the temperature, and how does that influence resistivity? Well, here are some resistivity curves that were found in experiments led by Jérôme's group in France some years ago. And as you go towards the insulator, you can see how the resistivity goes up in a T-square Fermi liquid fashion, but then reaches this maximum and then drops. And as it turns out, this resistivity maximum has been observed, but not completely understood at the time. To see what happens when you raise temperature in DMFT, let me actually show you this movie that my former student and current collaborator, Darko Tanaskovic, produced. So here is what happens. As you raise the temperature, the quasi-particle is destroyed, and the resistivity goes through the maximum. Let me now lower the temperature and show you more slowly how it happens. So now I'm lowering the temperature on the metallic side, and you can see now the resistivity is going up because you're activating across the Mott gap. But then there's a temperature where the resistivity reaches the maximum, and look what happens to the density of states. The density of states, which had a pseudo gap before, now starts to change, and you start building this quasi-particle peak, which represents those correlated electronic states at low temperature of the Fermi liquid. So there is a one-to-one correspondence between the thermal destruction of quasi-particles and the resistivity maxima that you have shown in DMFT, and that indeed is found in experiments. We extended this work to add some moderate disorder with Miloš Radonjić, who was a former student of Darko Tanaskovic some years ago. And this result shows two plots. One is, this is the density of states just on the metallic side of the Mott transition at different temperatures. And we see again, like what we show in the movie, as we raise the temperature, then this quasi-particle peak is destroyed. We add weak disorder, what happens? Well, what happens is that these Hubbard bands are slightly broadened. But and that means that the critical U is increased, but if we stay at the same distance to the critical U, the temperature dependence is almost identical. The Hubbard bands are slightly deformed, but qualitatively the behavior is almost identical, and even quantitatively almost the same. So that means that, again, in this regime, the main effect of disorder is just to broaden the Hubbard band, but it doesn't really affect quasi-particles very much in this regime where they are already very incoherent and being thermally destroyed. The resulting resistivity curves are also almost the same. So this is another example of how in this regime, which is rather far from the Fermi liquid, where the Fermi liquid is being thermally destroyed, you may call it a bad metal regime. In this regime, the disorder also plays a surprisingly little role. These resistivity maxima, in fact, show another curious feature, which is the fact that the temperature of the maximum, which corresponds to, as I'm trying to convince you, quasi-particle destruction, that temperature shrinks as we approach the transition, as it should, but the height goes up. What we noticed with Miloš in a paper published around 2010, 2012, that you can rescale these curves by the temperature of the maximum and by the height of the maximum, and they all follow the same scaling function. You can repeat the same thing in experiments. Here are some experiments by two-dimensional electron gases in silicon by Vladimir Dobrosavljevic some years ago. And you see, all these curves shown here on the logarithmic scale, they look almost the same. That suggests that this kind of scaling should work. And in fact, when you repeat our procedure, you get this collapse, which is in perfect agreement without adjustable parameters with our red DMFT scaling function predictions. This is an amazing agreement with your experiment. But what I want to emphasize here is that in this material, there definitely is disorder. You can see the residual resistivity in the experiment is not zero. In fact, it's not particularly small either. So we had to subtract that before we compare to theory. But then what we found is that the finite temperature component of the resistivity is very weakly affected by disorder. And when we compare the temperature-dependent part to theory, then we find perfect agreement, even though the theory had no disorder. So that means that the temperature, the thermal effects here in this strongly correlated liquid, yes.
Is that N is a doping? What's
well,
N?
as it turns, yes, this is N is the density of the 2D electron gas. As it turns out, in this case, you can tune the Fermi energy by changing the number of carriers. But as it turns out, it's believed that at low density, this is a Wigner crystal. But the Wigner crystal lattice spacing changes with density. So the system effectively stays essentially a half filling. So that's a little subtlety of the 2D electron gas. It's a little tricky. The mapping to Hubbard model is a little dubious. But very similar behavior is also found in materials which have definite bands and are sitting at half filling, like Moiré systems or Mott organics. Very good question. Thank you.
It's in fat transistor, yeah? It's like system.
Yes, this
in
is
this experiment. Yeah. Okay.
Yes, yes, it is indeed. So what I want to say is that even though there is some disorder in the system, these are high mobility MOSFETs, which were difficult to make. And in fact, before they were fabricated in Russia first, and then at IBM, people didn't really believe that there is such a transition. But now we believe that, in fact, this is something closely related to the Mott transition, not maybe exactly a Mott transition, but very close to it. So, so I try to convince you that in this high temperature regime, in a very broad range of parameters in the phase diagram, disorder doesn't play a big role except for modifying, shifting the transition by changing the bandwidth. Well, the situation is a little bit different than when you go to very low temperatures, where you approach a coherent Fermi liquid state, because one of the main properties of the coherent Fermi liquid is that it resembles in many ways non-interacting electrons, except that in the Fermi liquid, according to Landau, the carriers are not individual electrons but quasi-particles, or dressed electrons, but which are nevertheless at low temperature sufficiently dilute. They don't scatter much. They are long-lived excitations with spin 1/2 and charge 1, and they resemble a non-interacting electron gas in many ways. And if that is so, they propagate to the system as waves, and they should display all the interference features of waves. So we can look at that a little bit more detail, and the way we can do it in our theory is to apply DMFT to this disorder Fermi liquid regime. And if we do so, then we have to look at a system which is not translationally invariant, because the disorder can be different, the site energies can be different at different sites. And then if we set up our DMFT calculation, its main content is to produce a correction due to the interactions, to the wave functions or to the Green's functions, which is contained in a local self-energy. We still require the self-energy to be local to be able to solve this problem in an approximation, but we allow the self-energy to be different on different sites, which is very reasonable. It's also true in the CPA approximation, but we can also do this in a framework of a CPA or in a supercell approach. So either way, we have local self-energies which are different on different sites, and this portrays a picture of a Fermi, a low temperature that gives you a Fermi liquid, where the self-energy assumes a simple form. There is a finite zero frequency component, and then there is a linear frequency dependence. The slope of that linear frequency dependence defines a quasi-particle weight as in standard Fermi liquids. That quasi-particle weight is what goes to zero at the transition, and that means that the carriers or the quasi-particles are gone. This is what Brinkman-Rice said early on. But here we can find similar behavior at low temperatures in this Fermi liquid. So we have these local self-energies. The difference is that now the quasi-particle weights, as well as the zero frequency component, are now position dependent, and they acquire a certain distribution function. So there are two things we should look at. One is this Z, the quasi-particle weights. It turns out it's given here. Some results are given here. This is Z as a function of the site energy. And we can see that it depends strongly on the site energy, which means that there's a broad distribution of Z's. They all shrink as we approach the transition, but relatively speaking, the distribution of Z's remains broad or even broadens. So remember, when Z vanishes, this is a Mott insulator. So if you have a broad distribution of Z's, some regions are more Mott-like, some regions are more metallic-like. An additional feature of this Fermi liquid is renormalized disorder, which is given by the Bayer disorder plus a zero frequency component of the self-energy, and that gives you a renormalized disorder potential, which is what the electron sees on its travel. It turns out that the variance of this potential, or the width of this distribution, is what determines the conductivity. And so here we plot the variance or the strength of disorder as a function of u. We are fixing the disorder and then increasing u. We ask, what do the interactions do to the disorder strength? And we find, surprisingly, that the disorder width or the disorder strength actually drops dramatically as we approach the Mott transition. So these strong correlations provide a very strong screening mechanism where the disorder is reduced or screened. This is, again, something completely different from what Anderson anticipated, but is now actually well documented in several materials. For example, in these Murray materials, you can see that here, you see that there's very little variation as you're approaching the transition. The zero temperature resistivity doesn't change that much, but the final temperature resistivity is dramatically affected. This weak dependence on the distance to the transition at low temperature may be related to this. This requires further study. But I want to mention that this result is obtained for pure site disorder. It turns out the same theory if you had hopping disorder. The result is that the hopping disorder is not really affected or reduced by this effect. So the disorder is not going to be completely suppressed, but can be significantly weakened or as you approach the transition. And that may explain why approaching a transition where your kinetic energy, where your metallicity is dramatically reduced, that doesn't seem to affect transport too much. This is one. Yes.
This W is a measure of disorder.
That's the width. That's in the Hamiltonian. We have a distribution of disorder, and W is the width of this distribution.
Okay.
So this is just a strength of disorder. I use W for the strength of disorder. This is notation that was used by Phil Anderson in the first paper, and I continued. So some people use W for the bandwidth. Here, using it, D is the half bandwidth, and or the Fermi energy, and W is the disorder strength. Thanks for asking. This is important that people understand the notation.
If I have we're talking about chemical disorder, right?
This is site disorder. Site disorder. So I just took a broad flat distribution of site energies, which, you know, in for example, in the calculation that Maria did, these are renormalized by the Mott-Dellung effect, and so we do get even in her calculations that these site energies are broadly distributed, and so I just took a featureless distribution to start with, and then I'm approaching the Mott transition by cranking up Hubbard U. And then I find that this local effect, the Mott-Hubbard effect, which is unrelated to the long-range Coulomb interactions, is the repulsion between two electrons in the same orbital. That effect tends to strongly suppress disorder. And why is that so? Because you see, when you put disorder, you can understand it in this way. The local occupation should vary quite a bit, as we've seen, in fact, in Maria's calculation. Now, if you approach the Mott insulator should have the same occupation on each side. So you can understand that as you approach the Mott insulator, the density fluctuations should be suppressed. And in fact, that means that the renormalized disorder should also be suppressed.
Yeah, that'll be interesting to compare how the Madelung potential Madelung potential should have a distribution as well. How they are related to.
Absolutely, but you see, this is one of the big shortcomings of this theory that we've done. We've only used the Hubbard model. We never considered the long-range Coulomb interaction. I'm convinced that once we have sufficient disorder, the long-range Coulomb interaction is very important, but these calculations have not addressed that important issue. And that's what actually I wanted to project to this audience, that we have found some interesting results, but a lot is missing from this.
Okay, thank you.
So now, if we go further, and now I want to show you in real space what happens to how the system becomes inhomogeneous when we add disorder. The Fermi liquid becomes inhomogeneous, and I can plot in real space. So this is done now not in CPA but in a supercell calculation. Again, we have different site energies on different sites. We'll have different renormalized disorder potential, and as a result of this, the local density of states, or the amplitude wave function, which can be measured but directly by STM, can be plotted in real space. And we find that at the Fermi energy, it's extremely smooth. Very, very smooth. Why? Because this renormalized potential at the Fermi energy is the disorder is very weak, and the resulting density of states is very smooth. So the disorder is pretty much eliminated if you look at the Fermi energy. But what if we look further from the Fermi energy, which you can do in STM? You can look at electronic states away from the Fermi energy by applying a larger bias. And then what do we find? Well, you see, when you add the self-energy, you add the self-energy to the site potential at finite frequency, it acquires some strong frequency dependence. So instead of just the renormalized energy at zero frequency, there's a correction which is frequency dependent that depends on this quasi-particle weight. Now, I told you, I don't have these plots here, but I told you that the distribution of disease, quasi-particle weight, is very broad. And that means that the disorder, effective disorder seen at finite frequency is much stronger than at zero frequency. So you expect that the landscape that you obtain is very smooth at the Fermi energy and very rough away from the Fermi energy. So it resembles the airplane view of Tallahassee at the Fermi energy, just green trees, no hills. And the top one at finite frequency, very rugged, very large spatial inhomogeneities that you see, which more resembles Aspen or mountains in Colorado than Tallahassee. So this is a very dramatic effect. And this effect even gets stronger as you crank up correlations and you approach the Mott transition. So my point is that even if you take moderate disorder, some spectral features become extremely inhomogeneous, but you have to look away from the Fermi energy and not at the Fermi energy. This is something that Seamus Davis has obtained and observed in cuprates in very spectacular STM pictures. Of course, this was done in a superconducting phase, but here we are suggesting that this is probably a property of any disordered Fermi liquid, and there will be upcoming experiments now being done, STM experiments on moire materials with weak disorder, and so we look forward to testing these ideas. But this is a very strong and very strange effect that large inhomogeneities happen due to disorder in this Fermi liquid, but not away from the Fermi liquid regime. Now, try to understand this a little better. We realize that this effect is very robust, as it turns out, and we can ask what happens if we just add one impurity with a modest impurity potential. So we just put a single site, single impurity in the Fermi liquid and ask, what does this impurity do to the metal? Well, the answer has been provided by Jacques Friedel a long time ago. If you take a weakly interacting metal like silver, put an impurity, it creates these Friedel oscillations where on square lattice will give you this kind of long tails with this particular form for the square lattice. It looks slightly different on different lattices, but the perturbation extends far away from the impurity because you have a gapless Fermi system. This is what Jacques Friedel found, and this is what many STM experiments have confirmed. For example, Ward Plummer has become famous by doing such experiments where he observed these Friedel oscillations. What happens when we crank up correlations and we approach the Mott transition is something very dramatic. What we find is that the locally the disorder is strongly screened, but also the spatial extent of the region that's perturbed by the impurity is also shrinks to a very narrow region. And this is for the density fluctuations, which are induced. And here are the local quasi-particle weight fluctuations. So these are parameters describing the Fermi liquid. The Fermi liquid is perturbed, but when the correlations are strong, the region that's affected is very short. There's a very narrow region, of a very restricted region. And so some people call this a healing process, a healing length. Healing because the impurity is now not able to affect most of the Fermi liquid except in its immediate neighborhood. What does set the length of this neighborhood? Well, as it turns out, there's a correlation length that's associated with the Mott transition that grows only very close to the Mott transition, and it sets the scale for this healing length. So this is something completely different than what you find in weakly correlated metals. And this is very closely related to an interference process that's responsible for Friedel oscillations. And that term given by the Linhart function is now strongly suppressed by the interactions or correlations. And that means that all the interference processes in disordered Fermi liquids should be suppressed. This includes, probably in the presence of a finite number of impurities, the famous Schuller-Ronner effect. And but that perhaps explains why signatures of this Schuller-Ronner effect are very seldom seen in strongly correlated systems where we have a heavy Fermi liquid. So this is something that, because we can do the calculation at for one impurity, which is weak, this calculation can be done semi-analytically, and we have a pretty good understanding of how this happens. But when we have a finite density of impurities near a Mott transition, the same effect, now that we understand it better, is the same effect creates these large spatial homogeneities. And we find, therefore, that close to the Mott transition, the Fermi liquid is rather unstable and rather wild when even modest disorder is introduced. So this is something to keep in mind. Much more work is needed to test how robust is this prediction, theoretically or experimentally. We addressed this, some of it theoretically. We want to know what happens if you take a strongly correlated superconductor, like this TJ model of Qualter and Leo and the large N approximation, where you basically have something like DMFT. You can solve this analytically for weak disorder, and you find that the superconducting order parameter also shows something like field oscillations near impurities in the weakly correlated BCS limit. But once we turn on strong correlations, then again we find healing, and the other parameter is influenced only near the impurity, and most of the space is not affected. This has some dramatic consequences in momentum space. I'm not going to talk about this in detail, but I just want to mention that if you ask what does this do to pair breaking, there is a dramatic result. It turns out that Abrikosov and Gorkov, in their wisdom, said that magnetic impurities in D-wave, in S-wave superconductors, they are strongly pair breaking. But if you have high angular momentum superconductors like D-wave, then any impurity, including non-magnetic impurities, should be strongly pair breaking. And this is why Chandra Varma said early on in the early days of high TC that anyone who predicts D-wave superconductivity is mentally retarded. He was talking about Kotliar, who predicted this in his paper with Leo. Well, as it turns out, Chandra Varma was completely wrong, and Kotliar was totally right. And today we know that we have D-wave superconductivity in cuprates. The question is how? What was wrong with Abrikosov-Gorkov? Well, it turns out that this healing effect that I just described to you can be discussed in the framework of Abrikosov-Gorkov theory, and one can, which is theory just asking, what does very weak disorder do to superconductor? So we can add weak disorder to a correlated superconductor, repeat calculations, which are fully analytical in the framework of the large N theory, but we expect very similar results for DMFT. And then we find that this pair breaking is strongly suppressed due to strong correlation. So this may be the reason why D-wave superconductors don't exist in the real world when they're weakly correlated, but they do exist in many, many strongly correlated systems, not only cuprates, but now also pnictides, probably in Mott organics and now in more materials. So this is something very interesting, that the strong correlations have a very, very robust way to screen the disorder, to suppress it once they're strong, and that has many interesting consequences. So the overall picture of this disorder Fermi liquid is that there is when we have smaller interactions, then the Fermi liquid is pretty conventional. Once we approach the Mott transition, there's an intermediate range which has many unusual properties. I'm not going to talk about many of them here. There is something called the electronic Griffiths phase, which has some strange thermodynamic response. But I will just say here that this is a very inhomogeneous region where disorder has a very large impact on some physical quantities, creating large inhomogeneities. But to see this, you have to remain in the coherent Fermi liquid regime and for sufficiently strong correlations. Now, if we move even further, and now from the Fermi liquid regime approach the transition itself at low temperature, what happens then? Well, we know that experimentally and theoretically, Mott systems that have filling, they feature a first order transition at very low temperatures. This is only about a few percent of the Fermi temperature, but it still can be seen in many experiments. And in particular in Mott organics, you see a first order transition up to about 25 Kelvin. In that case, the Fermi temperature is about 2000 Kelvin. And in this, around this first order transition, you have phase coexistence as around any first order transition. And so in real space, you should expect domains of the two phases, just like in clouds, we have coexistence of liquid and gas. So let me now show you some results concerning this regime. So if we take again supercell DMFT, with weak disorder, and we look at the coexistence regime. This is what Marta Villagrán, who's a former student of Eduardo myself, has done. And we published a paper just this year on this. You can see here some snapshots of what the local density of states color-coded does as you approach the transition. We start from a metal towards an insulator, but the intermediate regime has these large scale inhomogeneities, just as I hinted. So blue is the metal, and red is the metal, and blue is the Mott insulator. So you see here domains of different sizes coexisting. And in fact, in 2 dimensions, Imre and Mott told us that this is particularly significant. We see in the simulation the evidence of that you, in fact, in 2 dimensions, weak disorder can create very large domains. And this is exactly what we see. So we find large domains of metals and insulator coexisting, even for weak disorder. This is completely consistent with the so-called Imre-Mott theorem, but it has huge consequences on our electronic system. Now, how do we see this in the experiment? And can we say something about transport? Well, to identify first this coexistence region is not so easy in experiments. And in a series of recent papers where I was involved together with the experimental group of Martin Dressel in Germany, we tried to look at experiments and to compare them to our theory and to try to map the phase diagram very carefully in all regimes. And from transport measurements, you can see the resistivity maxima give you this Brinkman-Rice line, which is a boundary between the quasi-particle regime and the high temperature incoherent regime. You can also see at low temperature T-square behavior. So you can map the Fermi liquid regime here at low temperature. You can see an inflection point as you scan pressure to go from an insulator to a metal. And the inflection point means this is on the log scale. Here there's a large resistivity drop, and this is the boundary. It maps the boundary where the Mott gap closes at final temperature. So this is the quantum window line that Anya discovered. So all these characteristic lines can be seen directly in experiments: the Fermi liquid line, the Brinkman-Rice line, the Windham line. But where's the coexistence region? It's not really seen here. Well, there are good news. In very recent work, Martin Dressel has figured out that you can do something different. He's actually an expert in optics, and they've measured the dielectric response in a different frequency regime, but in particular, at very low frequencies in the kilohertz range, which is pretty much almost zero frequency, they've measured the dielectric constant, and they found something truly spectacular. So this color-coded phase diagram shows the dielectric constant epsilon1, the real part of the electric response, across the phase diagram. In the Mott insulator, the electric constant is of order 5 to 10, very small, as any insulator, positive and small. It's slightly larger here at high temperatures, probably because there are some the other degrees of freedom in these systems, but it is a small effect. What is very interesting is that as you lower the temperature, below this Brinkman-Rice temperature, now I emphasize that this is determined from transport, this Brinkman-Rice temperature, resistivity maxima. When you go below that, suddenly the electric response changes from positive to something that's negative and very large. This is log scale. So there is a huge drop of the electric constant here where it becomes negative, and negative is exactly what you expect for any metal or Fermi liquid. So there is a huge effect on the electric constant. It completely maps this quasi-particle regime, even far outside the Fermi liquid regime. So note that this blue quasi-particle behavior, which is that of a metal, doesn't stop at the Fermi liquid boundary. It persists in the bad metal regime. So the boundary between blue and red, in fact, is the destruction of quasi-particles, not the destruction of the Fermi liquid. But even more spectacular is the behavior at low temperatures. Here, what you see is a region where the dielectric response is gigantic, colossal. Here, the dielectric constant can be, in some cases, as large as 50,000. So there is a gigantic peak of the dielectric constant to positive values, huge peak before it dips to negative values of a metal. So this is a remarkable discovery because it actually maps exactly the coexistence region. Another question is, can we understand this colossal dielectric response from the point of view of DMFT? Or so is it related to the coexistence region, or is it simply related to closing the Mott gap? You may imagine that as you close the gap, you're going towards the metal. Maybe the system becomes more polarizable, and maybe the electric constant grows because of that reason. Well, to answer this question, we worked theoretically with Yu-Ting Tan, who is my current graduate student, and with Martin Dressel, and we set up the following calculation. So first, we computed the electric response in an insulating phase. This is the red curve. These two dashed lines are the boundary of the coexistence region, and we see that as long as the insulating phase is stable, exists, that the electric enhancement, there is a tiny enhancement, but it's negligibly small. So this colossal peak, this is on log scale, not explained here, but there's a gigantic response here, which is unrelated to the behavior of the insulating phase. The metallic phase is even less influenced. Here is blue. This is the metallic phase where the electric constant is negative and large. So neither the insulating phase nor the metallic phase in the coexistence region show this. So this is not related to closing of the Mott gap. Instead, we expect in the coexistence region, according to Imre and Mott, to have large domains. How do we model this? Where we have to set up a resistor network, a random resistor network, where the fraction, the volume fraction of the metal and the insulator varies smoothly across the transition. And then we describe the complex impedance of the resistor and the capacitor by doing the DMFT calculations for the respective metallic and insulating phases. This is what we've done. But I can explain to you physically why why does the inhomogeneous situation lead to a huge dielectric response. Imagine that you are still, that the metallic regions, which are blue here, are still not connecting, but they are very large. So to get such a domain, which is represented by a resistor, we replace one of the capacitors by a resistor. Now we have a metallic domain. You see now when you apply an electric field, this entire region is now polarized, and it has a much larger dipole moment. If we make these metallic regions bigger, then the dipole moment that is formed is larger and larger. And this creates a huge polarization and a huge dielectric constant, as long as these regions still don't connect. And then you have an accumulation of charges at these boundaries. This is completely captured by our modeling, which we called hybrid DMFT. So we do DMFT calculations for the respective phases, and then on top of it, we set up a resistor network, and we use percolation theory to predict the global transport properties. The results are shown here, and they completely agree with the experiment. We do find in the coexistence region, which is shown here, this colossal electric response, exactly as in experiments, and you can really explain almost everything that's shown in the experiment from the point of view of this theory. I just want to show you, one more picture here. So we can also capture this drop of the electric constant over here. And we also see this huge peak in the electric constant. So pretty much everything is now completely understood. Yes.
I have a question. So some of your plot is the phase variant on the x-axis, you have like disorder. And the other is with pressure. So how they are related, disorder and the pressure?
Actually, I'm sorry for the confusion. I should have noticed this. W in these are the plots for this paper. They've used W for the bandwidth and not for disorder. This theory has been done in absence of disorder. The description of the two phases that I'm showing here are for the clean limit. In this picture, the only effect of disorder that we consider is the fact that we have phase coexistence. If you have a clean system, you have global phase separation. To get these large domains, you need some weak disorder. We found in the simulation, supercell simulation, that this indeed happens. But in this calculation, we've only assumed that there is a certain volume fraction of metal in the insulator, and when you took a model, they vary smoothly. And then we do a percolation calculation, but the components, these domains themselves, are taken to be without disorder. So in this phase diagram, we are tuning, in fact, the bandwidth and not disorder. So I'm sorry for the confusion. W is not disorder, is the bandwidth. So we go from an insulator to metal by increasing the bandwidth. So you see here, when the bandwidth is larger, then the correlations compared to the bandwidth is smaller. So this is now metal, and this is the insulator. So sorry for the confusion about the
Okay,
notation.
so bandwidth, actually bandwidth is related to pressure.
That's right. In these organic materials, you know, you have these big molecules, which are the wave functions are weakly overlapping. When you apply pressure, then the overlap increases, and there are DFT calculations demonstrating this, that the bandwidth is increasing as you. This is actually well represented by single half-filled band, and then by increasing the bandwidth, you're basically increasing the Fermi energy of your system by keeping the filling at 1/2.
Thank you.
Okay, very good. So this is what you obtain. So again, this is an example where we can understand even quantitatively the behavior of the system in the coexistence region, where it is extremely sensitive to disorder. There are large-scale inhomogeneities even for moderate disorder. We have theoretical and experimental strong evidence of this, and it has some spectacular consequences in the sense that it produces this colossal dielectric response, which is really an excellent way to map the boundary of the coexistence region. See, what's really interesting here is that the boundary of this region is extremely sharp. This is what exactly we expect when disorder is weak. It will really have a significant effect only pretty much in the coexistence region, and some weak effects very close to it on the metallic side, but most of the phase diagram is really not affected. And this is a characteristic of these Mott organics, where the disorder is very weak. These are very high quality crystals. There is very weak disorder, but nevertheless, the coexistence region displays these gigantic inhomogeneities and the resulting colossal response. So this is what pretty much it completes my tour around the Mott Point here. I've discussed various regimes, and I've shown you that some of them are not very sensitive to disorder, others are very sensitive to disorder, but the guess that Anderson made, that disorder and interactions are helping each other, is not at all correct. There's now good theoretical evidence for this, for various approximations, different theoretical approaches for the Mott transition, but also experimental evidence. And this is now an emerging picture, which seems to be very robust. What I wanted to kind of in a pictorial way stress here is that normally people think in terms of the electronic systems, at least conductors, in terms of the non-interacting picture, which works really, really well for good metals like silver and copper. Here you have, according to Landau, a dilute set of quasi-particles that very weakly scatter, and we can really think in terms of a renormalized non-interacting system. This is very similar to the behavior of a classical gas, like air, where you have dilute particles which scatter not very often, and the behavior, the equation of state, is very similar to that of an ideal gas. So just like air is very close to an ideal gas, a Fermi liquid is very similar to an ideal gas of fermions. This is great, but it's true, as you've seen, only at very low temperatures in a correlated system, and that range of temperatures where the Fermi liquid is coherent shrinks dramatically and becomes infinitesimal close to the transition. Elsewhere, the excitations proliferate, the thermal fluctuations can easily destroy the Fermi liquid, and then you have a behavior which is very different. You have a lot of excitations, they scatter very often, you have a very short mean-free path in this high temperature incoherent behavior, and the behavior of that quantum liquid is more similar to the behavior of honey, with huge number of scattering and huge viscosity than the behavior of a dilute gas of ideal quasi-particles. So this is a physical picture that now shares some similarities with some very fancy math of ADF CFT that people are doing. I'm not even talking about this. I just presented you a very simple-minded DMFT theory, which we understand all too well, but I think we were lucky here. It works really well for most systems. So for most Mott systems at half filling. So my conclusions are the following. DMFT, as it turns out, even in its simpler form, is not very sensitive to disorder, except in some special parts of the phase diagram. And this is now very well confirmed by experiments. We find that disorder tends to suppress the Mott effect. It suppresses the Mott insulator, whereas correlations, when they're strong, they tend to suppress disorder. So disorder and correlations, they don't like each other, they oppose each other. And this is something totally different than the early ideas suggested. But it's now well documented and well understood. They are many open questions. Not all systems are close to the Mott insulator. And also, there are other corrections which are not captured by single site DMFT. For example, there's super exchange, which is probably dominant in cuprates, that singlet formation has to be considered. You may need to do this in VO2. You may have to do it in phosphorus doped silicon. This is a challenge now for the future to add cluster corrections, intersite corrections to DMFT. And this is something where really monumental work has been done by Mark Gerald and his group that now is continued with Anya and other collaborators, where beautiful cluster methods can be used to go beyond the single site approximation. There are other interactions, as Yang pointed out. There are long-range Coulomb interactions, there are electron-phonon interactions, and those other interactions, which we didn't even talk about here, they are probably dominant in systems which are not close to the Mott transition. In these more rare systems, you can work at different fillings, and you can in fact see some very different physics and some phase transitions, metal and soil transitions that are totally different than the Mott transition. That's a challenge for the future, to tackle long-range Coulomb interactions, electron-phonon interactions, and magnetic orders coming in to create some sort of polaronic effects as a response to disorder. This is a huge challenge, and I really look forward to doing part of that work here within this collaboration. Anisole localization, what is the big role of this? Well, even for Hubbard models and strong disorder, anisole localization plays a role. We've done a lot of studies of this. I didn't describe that here. That probably is incomplete, and that may really be, the results may be strongly affected by intersite spin correlations and corrections to single site DMFT. So this is another big challenge. And finally, many of these inhomogeneous states that we find are probably metastable. There's a lot of metastability, glassy behavior, non-equilibrium behavior. Some of these bad metals may feature really weak thermalization. Zagana Popovic in our lab has now a beautiful experiment showing how, when you screen the Coulomb interaction through a screening gate, you can really pretty much kill thermalization and find something which is closely related to many-body localization. So there's a lot of exciting physics that remains to be addressed, but at least we have a starting point where we understand something rather well, and that something is the vicinity of a Mott transition with weak and moderate disorder. So I'll stop right here, and thank you very much for your attention.
Thank you, Vlad. So let's have some questions. Anyone?
Yeah, just a comment. That was a lovely talk. I really appreciate it. And I think I followed the first part a lot better than the second part. But that's what happens when you don't do physics every day. But one system that I know of, which is in the regime of extreme disorder, it's a ternary system of a high entropy alloy. So this is happening around equiatomic contribution, concentrations in nickel, cobalt, chrome, and you can go to the ideal system and then move away a little bit on either side by changing the concentration of chromium. And it was discovered a long time ago now. Brian Sales at the lab did some very nice experiments that show the occurrence of what has all the characteristics of a quantum critical point. And but we're now in the regime where you have extreme disorder, and it seems to be driven by that. But obviously the electrons are doing something very odd. You get, linear resistivity. There's a particular concentration. So it was exciting at the time because we thought that you've got this system here where you have a control variable, namely the concentration of chromium, and you can just, there's no fancy anything, you just make the samples and measure the darn things, and just by changing the concentration of chromium.
This is wonderful. Question, is this, from what it sounds, this is not close to any Mott insulator.
No.
Not at all, right?
It's-
So this is probably metals close to something like a disorder-driven insulator. Right?
Yeah, well, yeah, I think it's a little bit, I think it's still not properly understood what it is. But what happens is that the other thing that's happening in these systems, because they contain metals that are all want to be magnetic in some form or another, right? So nickel, cobalt, and chrome. Nickel and cobalt are perfectly good ferromagnets, but chromium is an antiferromagnet. Right, and you're changing the concentration of the antiferromagnet. So the presumably, and if you do calculations using KKR CPA of the state as a function of chromium concentration, as you get to this quantum critical point, the magnetism is just completely suppressed. So although all three elements are magnetic, this thing, there is no magnetism in this damn thing. And
is it clear that they don't have spin glass behavior of some kind?
Probably pretty clear by now, yeah. And so
it's very interesting.
It's a very odd system. Brian Sales worked with some other people who kind of blame this on just extreme disorder, and I think it's probably worthy of someone like yourself perhaps just taking a look and see.
Yeah, I'd love to know more about this. This is exactly what I'm interested in. In fact, this is fantastic. Sounds like a fantastic system. And I should have known about this, but I would love to hear more.
No, it's in the metals business, and but
question: Why is there insulating when all three are good metals?
Yeah.
You think that when you're mixing three metals, you should always get a metal?
Well, what it is it's actually a bad metal, is what it is. So it's not insulating. It's just that the resistivity just is linear. Well, you can find a concentration which is just linear. The magnetic susceptibility has its sort of characteristic behavior as well. So it's if you do KKR CPA, you can see that with zero chromium, right? It's just a mixture of nickel and cobalt, perfectly good magnet, right? And now you can track how the magnetism, what happens to the magnetism as I increase chromium, right? And if you do KKR CPA, surely the magnetism is disappearing. But it's not. But it's disappearing linearly with concentration. Right. When you get close to this point, whereas when you measure it, it's actually the moment is disappearing logarithmically. So this is not a trivial matter. It's the difference between a linear decrease and a logarithmic one.
So how can I learn more about this?
Well, I'll find you some references, but the first one was something published back. The first reference to this was back in 2016, and it was just in Scientific Reports, and the first author is Brian Sales.
Okay, I'll look for that. This is really interesting.
My name is on it, and German Samolyuk and various people.
I'll definitely look into it. I actually believe that in some of these reasonably good conductors, and when you add strong disorder or magnetism or things like this, that there should probably be some strong polaronic effects. Maybe many people talked about this, and I think this is a very robust phenomenon that may lead to actually generally to some pseudo gap opening in the density of states. But have they seen? Is this known? Do they have some, like if you do STM or if you do tunneling, do they have some gap starting to open or no?
the short answer to that is I don't know. I don't know. I don't know whether it is known. But you know, you're certainly not going in any of these systems going to get in any of the theory that we know, we don't get band gaps or anything like that, right? The density of states is quite high. Nothing weird is happening in that regard. So it's well, so far as we know. And,
all right. Well, definitely. Let me have a look at this, and let's discuss this in more detail once I get up to speed. But it sounds very interesting.
I have one small question.
Okay.
Yeah. So you talked about disorder and interaction. On top of that, if we add kind of Peierls physics, what would you expect?
Well, you know, this is a very good question, and it's a long-standing question. Material where you do have prominent Peierls physics is VO2. I actually have some papers on VO2. Yeah. And what happens in that case is that pairs of, for example, vanadium is a strongly correlated atom, and in a Mott insulating phase, you'd expect a spin 1/2 sitting on each vanadium. When you bring them together in a dimerase fashion, it turns out that they start to form a strong singlet, and this effect can be captured in a DMFT fashion if you do a cluster calculation where you take basically a unit cell with 2 vanadium atoms, because now, you know, once you have dimerization, your unit cell has 2 vanadium atoms. So if you take that and you do DMFT, you may call it cluster DMFT, but you have 2 vanadium atoms in the unit cell. Then the self-energy doesn't have only a diagonal component, but it has an off-diagonal component, sigma 1, 2, renormalizing the hopping between these 2 atoms. And that can have a very profound effect. What we've discovered in our papers is that when you are so if you have a coexistence region, for example, the metallic solution, this self-energy, the off-diagonal self-energy, which is beyond the local self-energy. So the off-diagonal self-energy in a metal is very small, but in the insulator it becomes very large. It renormalizes at 0 frequency the hopping. So when you have a dimer and the hopping, it becomes very large, you form bonding and anti-bonding states, and that helps open a gap. So it's believed that the gap in there's a lot of LDA plus DMFT work also done by various people, including Kotliar and others. That the reason why VO2 is insulating is actually strongly assisted by this Peierls mechanism, which says that, but you cannot capture this in a single site approximation. You have to do this 2-site cluster calculation. So you're allowing this intersite singlet formation to strongly assist the formation of an insulator. So this is an example where some strong correlation effect is important, but you cannot capture it in a single site approximation. So that's why this is what I believe happens there. There's good evidence now, experimental evidence, that this is happening. But another system where something similar could happen if you consider a broad class of doped semiconductors like phosphorus doped silicon. In the insulating phase, each phosphorus has a spin 1/2 local moment, and you can call it a random Mott insulator. Now, these two, because it's random, each site has one nearby neighbor, one nearest neighbor. And as it turns out that these neighbors, they form singlets. This is now a well-documented, well-understood process in doped semiconductors, which explains the magnetic response in the insulating phase. This is a famous Batten-Lee theory. So this is another example where singlet formation on pairs of sites plays a big role. And this is something which you may call a generalized Peierls effect, right? The point is that, pairs of sites form a dimers. And that could enhance, in some cases, like in VO2, that can also be coupled to the lattice. And in VO2, it actually, gives you this structural transition from a rutile high temperature phase to a monoclinic B1 phase, M1 phase of VO2. But I think that there is a more general context, and I believe that these intersite spin correlations, which are not captured in single-site DMFT, they maybe are not so important on triangular lattice, which is strongly frustrated. But I believe that when you add disorder, you're breaking this translational invariance, and each site will acquire one preferred neighbor, and then they will lock in singlets. So I think corrections to single site DMFT will be more important in disorder systems than they are in a clean limit. And I think this is a big open area that needs to be investigated carefully.
Yeah. I mean, I know people talked about a lot for the VO2 like competition between Peierls physics and interaction, but people doesn't talk about much on the effect of disorder on that picture. So I'm not found.
Well, yeah, this is that's true. The disorder has not been so much discussed. What I'm trying to say is that the doped semiconductors have extremely strong disorder. You can think of it as a lattice where the sides of the lattice are completely randomly placed, and because the overlap of these hydrogenic wave functions is an exponential function of distance, you expect that the hopping elements are broadly distributed over many orders of magnitude. So this is an example of extremely strong hopping randomness. Mm-hmm. And because of this reason, the super exchange interaction J is also broadly distributed, and there will be some bonds which have very large super exchange. So in that case, you find something that is actually reminiscent of VO2, that basically the low temperature spin configurations form pairs of singlets, which are randomly placed because of disorder. And this is something in principle that you can think of this as a very random version of VO2.
Yeah.
Now, I wanted to mention something. I'm actually working on this, that in phosphorus doped silicon, it's difficult to control the positions of atoms. They actually cook these samples, they melt them, and then the phosphorus atoms, they're completely randomly placed in a silicon lattice. But right now, there is actually people both here at NIST in this country and Sandia, and also in Europe, a group of Geb Epley at Paul Scherrer Institute, they can implant with STM these phosphorus atoms on the surface of silicon at positions that you can specify. So they could make a periodic lattice, a triangular lattice, but they could make a dimerized lattice to mimic VO2. And then they could actually introduce some randomness. And by doing this, these are called metamaterials. You could actually tune yourself in increasing the disorder, tuning the dimerization, tuning the disorder, and exploring how this influences the system. This is actually a very, very promising direction. And I started already to work on an ab initio approach to the hydrogen lattice, motivated by this work. And I think it has a lot of future, but it's also technically very challenging. And I think really another beautiful, artificial system that can test many ideas.
Yeah.
Okay.
Thank you.
Any other questions? Let me stop the